Hello, this is my Lab 3 presentation regarding black holes. This lab explores motion experienced by an object given gravitational force, in this case resulting in orbital motion. It includes a real-world demonstration rooted in the second law of motion, as the net force is equal to the force of gravity. This law is also known as the momentum principle and is applied multiple times in this lab, including to analyze the properties of the planet's motion, like the change in momentum in parallel and perpendicular components. The gravitational motion formula is also used to take the motion of the object and solve for the mass of the black hole. The motion for the planet is generated based upon my email, and I coded formulas which would both demonstrate force vectors but also would solve for values such as the mass of the black hole. After executing the experiment, I found that the computer model was able to provide a mostly consistent value for the black hole. However, the greatest deviation from the average force occurred when the star was closest to the black hole. The starter code was provided that would generate the trajectory for the star around the black hole. Simulation is seen on screen now. The values for velocity were extracted from the provided dataset. All other values were solved from these values. This includes momentum as well as the parallel and perpendicular components for net force and dp over dt. Finally, I extracted the mass values from using additional calculations, including a modified gravitational force formula. This results in an average mass of 1.46 times 10 to the 34th kilograms. The provided graph plots the calculated mass of the black hole and average mass during this time. Ignoring the small brief spikes in calculated mass, the mass trends upwards as it approaches the black hole, swiftly drops as it passes the black hole, and then continues to trend upwards. Seen here is my completed glow script code, which was written in VPython to generate accurate position data. I input my GT email and provided the mass of the star. I then took the position data for each time instant and solved for the delta V for all other points. This included the initial and final momentum. dv over dt, final, fnet, and more were solved. I also had to set the delta t in terms of 1 day, which had to be set in seconds. For all other values, they were calculated using dp over dt, parallel and perpendicular. I was able to solve these using I was also able to solve for the instantaneous mass of the black hole using an application of the gravitational force formula. I then solved for the average mass during the entire time period of one complete orbit and visualized the force components using arrows. On screen now is a screenshot of my simulation. On the left is my model during execution, and on the right is shown completed. You'll see the arrows that show the direction of the net force and the parallel and perpendicular components applied on the object. The output data can be found in the previous observation slide. The simulation can be found on the links on screen and are included in the submission. Because the net force was calculated through the assumption that dp over dt is approximately equal to delta p over delta t, the accuracy of the experiment could be improved if the delta t was decreased. This would mean that those two values would result in being closer, making the resulting data and calculations even better represent the situation. However, besides this, there are very few steps that could be taken to improve the experiment because all the data was provided to us, meaning that there are very few opportunities for errors to arise. Further thought. In this lab, we used the net force and rate of change of momentum as synonymous. However, this is only because we were able to assume that in the case that for a relatively small delta t value. In reality, the rate of change of momentum and its parallel and perpendicular components could be non-constant during the delta t interval and thus would not be equal to the instantaneous net force in parallel and perpendicular components. This is seen with the fact that the net mass calculations, like others, can only be calculated and printed for every delta t. If the motion of the observed star were to remain unchanged, then would it be possible for the black hole to be changed? The mass of the black hole to be changed? We know that we would be able to note that the new black hole would have the same mass as the original. This is possible because the only force that is in effect here is the gravitational attraction between the star and the black hole. This attraction can be defined by the formula Fg equals G big M small m over r squared times r hat. It can be observed that the mass of this black hole that would be using includes the big M value, which implies that the mass of the black hole is unchanged, as if the mass changes, then the force would also change. And this would result in the star's motion changing. Thank you.